Hi, and welcome to this linear algebra crash course. In fact, welcome to control and estimation theory. This must be the first video you are watching. And let me start by saying that in this module, we will be following the flipped classroom approach. Now, what is that? Typically, students come to class, they attend lectures, they take notes, and then they go home and they study by themselves. Here, we'll do things in exactly the opposite way. So, you'll be watching lectures like this one at home, which you can do in your own time and space. You can do it in the morning, late at night, whatever you like. You can pause the video or you can watch it again, things you cannot really do in a classroom. And then, when you come to class, you might not have understood everything, that's absolutely fine, but we'll spend our time together in a more productive way. We'll be solving problems, we'll be answering your questions, we'll be having discussions, and this way you will eventually assimilate the material, you will understand the material a lot better and a lot deeper than if we followed the traditional, the conventional teaching approach. So let's move on now to linear algebra. This is a linear algebra crash course, so the objective is mainly to brush up your undergrad linear algebra and somewhat touch upon things that are more advanced. But we'll start with basic things like, for example, vectors and matrices. So we'll start with the basics, vectors and matrices, and then we will move on to vector spaces, which are slightly more advanced, but the final destination is linear equations ax equals b, where a is a matrix and x is a vector. So the final destination and main objective of this crash course is to make sense of linear equations. But step by step, let's start with part 1, vectors and matrices. And let's start in particular with vectors. What is a vector? A vector is a thing like this. It's a sequence of numbers where you have the first number, the second number, the nth number. Simple as that. For example, take x equals 5, 6, 10. 3 numbers in a row. That's a vector. These numbers can be real or they can be complex. So we talk about real vectors and complex vectors. And n here is called the size or the length or the dimension of the vector. So that we don't have to write down x is a real vector of dimension n. Instead of writing this down, we write x is in r to the power n. Or if you have complex numbers, if you have a complex vector, you denote this as x belongs to c to the power n. What can we do with vectors? We can add them, we can subtract them, and we can do a few more things we'll discuss later. But say you have two vectors x and y. Say you have x and y, which are in Rn. Recall again, this means that they have a dimension n, and the elements are real numbers. Then we can define x plus y. You add two vectors, the result is a vector. What vector is it? It's this one. The first element is x1 plus y1. The second element is x2 plus y2, and the last element is xn plus yn. I will not give examples now, because the objective here is not for you to fully understand every single aspect of what I'm saying, but to be exposed to the material. If there is anything you don't understand, write it down, come to class, and we'll discuss about it. So this is addition here, and likewise you define differences, x minus y. Sorry, just a moment. There is another thing you can do with vectors. Actually, you need a vector and you also need a number, or a scalar, as we say sometimes. A scalar is a synonym for a number. So you have a number a, you have a scalar a, and you have a vector x. You can multiply the number by the vector. This is called actually scalar product, a times x. And the result, okay, you could have guessed, but it is ax1, ax2, ax up to axn. Simple as that. Now, last thing here, there is a special vector called the 0 vector. It is a vector of 0, simple as that. Now, some people find this confusing, or it actually might be confusing in different contexts. This 0 here denotes a vector, but it happens to be the same exact symbol as the number 0. If it is very clear from the context, then you can use 0 to mean a vector. If it is not clear from the context, or if you don't feel comfortable with this, you can write 0 subscript n to make it clear that this is a vector of zeros, a vector of n zeros. Right, vectors. So we can add two vectors, and we can multiply a scalar by a vector. But can we multiply two vectors? Does it make sense to talk about x times y, where both x and y are vectors? Well, let's see. There is a thing called the inner product. The inner product of two vectors, so take x and y to be in Rn, the inner product is first of all denoted like this. You could denote it by x dot y, but this notation is slightly more established, x, y. Before we move on, let me say that the choice of the article here, we say an inner product, we don't say the inner product, is important. There is not a single inner product. I can define an inner product if I feel like it. I'll show you how to define your inner product if you feel like it. But in any case, what makes it an inner product, there are really many inner products. What makes it an inner product are these four properties. Let's go through them one by one. First of all, symmetry. X times y is equal to y times x. Makes sense. Then, if you have the vector a times x, recall, a is a number, a scalar, x is a vector, ax is a vector, comma y, so this means that I am multiplying the vector ax by the vector y. You can move, so what the second property says is that you can move this a outside of the product, like this, a times xy. The third property, which is also referred to as linearity, number 2 and number 3 actually are the linearity properties of the product, goes like this, x plus y times z. Yes, you got this right. It's like you multiply x plus y times z. This is the distributive property in a way. This is x times z plus y times z. So this is another property that an inner product must satisfy. And the last one is that x times x, now please be very careful with that. We say x times x. You can say that. You can say x times x. But you can never, ever write x squared. X squared doesn't make sense. So this doesn't make sense. Don't ever write vector squared. If you want to, sometimes what you really want to do is this, x times itself. This is legit, you can write it. Right. Now, x times itself must be positive unless the vector is 0. If the vector is 0, 0, 0, 0 times itself is equal to 0, the 0 number. I'm not sure I made this clear, but when you multiply two vectors, the result is a number. So you get a vector x, you get another vector y, you multiply them, the result is a simple, humble number. You multiply two vectors, you don't get a vector, you get a number. And by the way, once again, this is called the inner product of two vectors. Moving on, a few examples. There is a standard inner product we use quite often, although, I'll say this again, There are more. I'll give you an example right away. But the very, very standard inner product is this. X times y is x1, y1 plus x2, y2 plus x3, y3 up to xn, yn. There are more inner products. But before we discuss more about this, you can do this as a little exercise. You can verify that this definition satisfies, this definition over here, satisfies the four properties, the four necessary axioms or conditions that make this an inner product. So is this really symmetric? Is it true that xy is equal to yx? You can check for yourselves. Is it true that when you have ax comma y, you can move a outside ax comma y? Is it true that x plus y comma z equals to what it should be? Check it here. Is it true that this is satisfied? Is it true that x comma x is positive, for example, unless x is 0, in which case it is 0, and in no other case actually? Well, let's do the last one together very quickly. So just give me a second to delete all this. So is it really true that x comma itself, x times itself, is positive? Well, we don't know, but we are given a formula here, folks. So this is this is x1 times x1 from here. x1 times x1, so x1 squared plus x2 squared plus and so on and so forth plus xn squared. So how does this look? Is this positive always? Well, x1 is positive unless x1 is 0, and then it is 0. Then x2 is positive unless it's 0, and so on and so forth. So all these things, these are squares. The square of a real number is not negative. It can be 0 only if the number is 0, but otherwise it's positive. So all of these are positive numbers unless they are 0. So indeed, this is positive. Positive. It's not 0 unless x1 is 0 and x2 is 0, and all of them are 0. So we proved the last property. But now, a very simple example of a different inner product is the following. This is another inner product. It goes like 10x1 y1 plus x2 y2 plus x3 y3 plus xn yn. This is a fine inner product. It satisfies all four conditions. And a very important thing to note is that if you take two vectors, x and y, they can be different, and you multiply them and you get a 0, this does not mean that either x is 0 or y is 0. So there are some differences between the multiplication of vectors and the multiplication of numbers. What does this mean? We'll discuss later. Let me give you one more example here, just to make the whole concept of an inner product slightly clearer. Take x to be 1, 1. It's a vector with two elements. Take y to be 1 minus 1 and multiply them using the standard inner product we talked about earlier. So use this formula over here. Okay, use this formula and multiply them, x times y. So you will see that you multiply the first element of x times the first element of y, and then you multiply the second element of x to the second element of y. And if you do the math, you end up with a 0. So look, we started with the vector 1, 1, and then the vector 1 minus 1. None of them is 0. None of them even contains a single 0 as a coordinate, and the result is 0. So be careful. Next question, can we measure the length of a vector? So we tend to think of vectors often geometrically. This is x1, for example, this is x2, and this here is a vector with coordinates, let's say 3, 4. But what is the length? What is the length of this vector? How big is this vector? We'll answer this right now. To measure how big a vector is, we use an instrument, we use a tool which is called a norm. We talk about the norm of a vector, we denote it like this, x norm, and this measures how big the vector is. The norm of a vector must satisfy 3 properties. The first one is that it must be positive or 0, we say non-negative, it must be non-negative, and in particular, if the norm is 0, if the vector has a 0 length, then it's the 0 vector. No other vector than the 0 vector has a 0 length. The second property is that if you scale the vector, if you do a times x, if you multiply your vector by a number a, then the norm of ax is equal to the absolute value of a times the norm of x. And an immediate consequence of this, let me show you, an immediate consequence of the second property is that if you do the norm of minus x, so the norm of minus 1 times x, what is that? This is the absolute value of minus 1, 1, times the norm of x. So there, the norm of minus x is the norm of x. Does it make sense? Let's see. So this is the vector x, and this is the vector minus x. Don't they have the same length? Yes, so that's what this suggests. The norm of x is the norm of minus x. And the third property, I don't want us to spend too much time on that, is the triangular inequality. The norm of x plus y is less than or equal the norm of x plus the norm of y. But again, I don't want us to spend too much time on that. There is a very, very, very popular norm. This is the big rock star of all norms. It is the Euclidean norm. The Euclidean norm. And what is that? It is the square root of x1 squared plus x2 squared plus and so on up to xn squared. We note this norm like this. There is a 2 as a subscript. There you see we write norm of x 2. Some people call this the 2 norm. Most people call this the Euclidean norm. There are other norms, however. There is this one called the 1 norm, which is norm of absolute value of x1 plus absolute value of x2 plus and so on and so forth plus the absolute value of xn. And there is the infinity norm, which is just the maximum of the absolute values. And there are more, really. There are more. I don't want to give you a huge list of norms, but these 3 are the most popular ones. But this is the king of all norms, the Euclidean norm. Right, moving on. If you give me an inner product, I can make a norm. This is how I'll make it. Take the inner product here, multiply x by itself and put it under a square root. This defines a norm. We say that this norm is induced. This norm is induced. I'll write it down. Norm induced by a given inner product. And here is a thing to keep in mind. If you give me the inner product to be the standard one, if you give me the standard inner product, what is the standard inner product? Let's recall x comma y is x1 y1 plus x2 y2 plus and so on plus xn yn. I can use this to make the following norm. Norm of x is equal to the square root of x times itself, where again this thing here is the standard inner product. I'm saying this, I'm repeating this because there are many inner products. So we have to underline this. The standard one. This will be the square root of x1 squared plus x2 squared plus xn squared. What is that? I'll take it to the previous slide. This is the Euclidean norm. This is the Euclidean norm, norm of x1 squared and so on. So the Euclidean norm is the norm, sorry, just a moment, is the norm induced by the standard inner product. Right. Some very useful properties, these are super useful properties of norms, and we'll be using them all the time in this module. These two in particular. Take an inner product, this one, and use it to make a norm, this one. Once again, you forgot, I'll remind you. What is this norm? This norm of x, let's say, is the square root of x times itself. Or what is the same? You can write norm of x squared is x comma x without the square root. Now, norm of x plus y is equal to the first term squared norm plus the second term squared norm plus twice the product, x times y. Well, this is reminiscent of a standard property from basic high school algebra. But how did this identity come about? Why is it so? Let me give you the proof of the first one, and then you can do the second one as an exercise for yourselves. So x plus y, norm squared. What is this norm squared? Here, look. This is the squared norm, the inner product of a vector with itself. So, this is x plus y times itself, times x plus y. The inner product is linear. Every inner product is linear. So this is what we can do. We can multiply x times x, then plus x times y, plus y times x, plus y times y. Just a moment, I'm running out of space. I'll move this a little to the left. There. Now x times itself over here, we've written this here, x times itself is x norm squared, norm of x squared, plus likewise here y times itself is norm of, norm of y squared. And then we have xy, and then we have yx. But the inner product is symmetric, so these are the same exact thing. So 2 times x comma y, x times y. And there you go, this is the first identity. Okay, the second one is not a big deal, but you can do this as a very easy exercise. We don't need this now, we don't need this definition. I will just give you the definition so that it will not be entirely new and strange to you next time we'll need it. We'll need it in a few weeks from now, but I'm just telling you to keep it in mind. So suppose that you have a two-dimensional vector, and this is x1 and this is x2. We said that the norm of a vector measures how big, it measures the length of a vector. The ball that corresponds to a norm is the set of points that have a distance from 0, a norm, a magnitude, have a magnitude less than r. That's why we call it a ball. That's why we call it a ball. We don't call it a circle, we don't call it a sphere, we call it a ball, and the reason is that it contains this shaded area. If you say sphere, you're talking only about the outside, the boundary of this set. Okay. So this is what we call a ball. Anyway, there is nothing else to talk about here. And this is really all I had to tell you about vectors. I don't think there is anything else we'll need when it comes to vectors. Quick revision. It's not much really. We said what a vector is, how to add vectors, how to subtract vectors, what happens if you multiply a vector by a number. We defined the zero vector, then we introduced the concept of an inner product, how to multiply two vectors. The multiplication of x times y gives you a number. This multiplication must satisfy these four properties: symmetry, linearity, and positivity. Then inner products. There are many. There's many of them. Too many actually. The standard one is one that we will be using heavily. We'll be using this all the time, and it is as simple as this: x1, y1 plus x2, y2 plus xn, yn. But there are more inner products. The inner product is 0 does not mean that one of the two vectors is 0. We can measure the length of a vector using a norm. And we have these two very important properties. And the ball. Okay, don't overthink. Don't overthink this. We'll need this in a few weeks from now. Matrices. What is a matrix now? A matrix is a two-dimensional array, or you can think of it, you can call it a table if you like. This is like a table of numbers where we have rows and we have columns. Simple as that. So this has 2 rows, 3 columns. We say that it is a 2 by 3 matrix. The space, the family, the set of all m by n matrices is denoted like this: r to the power m by n. Instead of having to write A is a matrix with 2 rows and 3 columns, you write A is a matrix with 2 rows and 3 columns, and that's your job done. Okay. The I, j element of a matrix is denoted by ai, j. Ith row, jth column. Now 1, 2, 3 and 4, 5, 6, check this out. 1, 2, 3 and 4, 5, 6 are the rows of A. On the other hand, 1, 4, 2, 5, 3, 6 are the columns of A. So rows, columns. If we have a matrix that is n by 1, this is essentially a sequence of numbers. N by 1 means that A is like this. There is a number here, a number below, and so on. N rows, 1 column. But this is essentially a vector, and in fact we call this a column vector because it is just 1 column. And on the other hand, we have a row vector. You can guess what this is, how it looks like. It looks like this. It has 1 row and it has many columns with only 1 element. And then one more definition. If a matrix is n by n, then we call it square. If it is not square, we call it rectangular. Now the transpose of a matrix, take this matrix A, which is 1, 2, 3, 4, 5, 6, take the first row and make it into the first column. Take the second row and write it downwards. That's the transpose of A. Simple as that. Now if A is a matrix of dimension 2 by 3, yes, you figured this out. A transpose is a matrix of dimension 3 by 2. So the dimensions get swapped. Just a moment. If you take the transpose of the matrix and, so to speak, nothing happens, then the matrix is called symmetric. So this is the case if these elements are the same. These are the same with one another, then this is really a symmetric matrix. Needless to say, only a square matrix can be symmetric. And of course, because we are a little lazy, instead of writing A is a symmetric matrix, we write A is a symmetric matrix like this. Blackboard style S to the power n. A is symmetric. Some famous matrices, some celebrated matrices. You must already know the identity matrix, which is like this. It has zeros everywhere, but not on the diagonal. On the diagonal, this is the main diagonal, we have 1, 1, 1, 1. Then second famous matrix, the celebrated zero matrix of dimension m by n. If you're confident that it's clear to you that this is a matrix in the context you're writing, you can simply write 0. If it is not clear to you, then you can also write 0 subscript m by n. Also, if a matrix has this form, look, some numbers on the diagonal, not necessarily 1, 1, 1, 1, anything you like. It can be something like this, A equals 5, 6, 100. This matrix is called, sorry you can't see it there, this matrix is called diagonal. It's a diagonal matrix. So once again, the identity matrix is a famous matrix, the zero matrix and the diagonal matrices are very famous. Also, you have lower triangular matrices where you have some numbers on the diagonal and below, but not above. Above you have zeros. Okay, 0 is a number. I mean, you have non-zeros below the diagonal, and on the diagonal above you have zeros. For example, L can be like this: 1, 0, 0, 2, 5, 0, 9, 10, 11. Above the diagonal, so this part of the matrix is occupied by zeros. This is called a lower triangular. Likewise, we have upper triangular matrices where we have lots of zeros below the diagonal. What can we do with matrices now? We defined what a matrix is. We described a little taxonomy of matrices, like types of matrices, like diagonal, symmetric, and so on. You guessed this right. We can add them. We can do A plus B. And how do you do A plus B? The same way as we defined A plus B for vectors. You add the corresponding elements. Needless to say, the dimensions must be compatible. So A is m by n, B is m by n. You cannot add apples plus oranges. You have to add m by n matrices like 2 by 3 plus 2 by 3 matrices. And likewise, if you had here a minus, you could define A minus B in exactly the same way. It would be the differences of the corresponding elements. Moving on, same as what we did with vectors, guys. We can multiply a scalar. C is a scalar. A is a matrix. C times A is a matrix with elements. C times each one of the elements of the original matrix. Now, we can multiply a matrix by another matrix. But I want your full attention here so that we don't make any mistakes. So, A is a matrix M by K. B is a matrix K by N. Did you see that? Here we have K columns and B has K rows. So I'll write it with big letters here. M by K, and then I'm doing K by N. This is my A matrix, this is my B matrix. And we're multiplying them, and the result, it says, will be the matrix AB, which is M by N. So the result is M by N. What the product of two matrices is not. When you have a 2 by 3 matrix and you have a 4 by 5 matrix, you cannot multiply them because 3 is not equal to 4, So AB doesn't make any sense. We have incompatible dimensions. Actually, for example, in MATLAB or in Python, if you attempt to multiply matrices that have incompatible dimensions, you get exactly this error message. Now, another thing, what is the product of two matrices? What the product of two matrices isn't? Say that you have A, which is 5 by 5, and say that you have B, which is again 5 by 5. So you are allowed to do AB, you are allowed to do B times A. These two things are not necessarily the same matrix, and usually the result is different. AB is in principle not equal to B times A. And there is an exercise in the handout where I'm giving you two matrices and I'm asking you to do AB, then do BA, and check that the result is significantly different. But all that said, what is? We said what the matrix product is not. But what is it really? Now, take a matrix A and say that this matrix A has these rows. Row, row. So the rows of A are the vector A1 transpose, because it's horizontal, it's a row vector, AM transpose. I'll give you a concrete example here. So say that A is 1, 2, 3, 5, 6, 7. So this is the first row, row 1. This is the second row, row 2. So this vector 1 to 3 is A1 transpose, and this is my A2 transpose. And take a matrix B, and now in B I'm focusing on the columns. So B1 is the first column, Bn is the last column. What is the product? The product is a matrix like what you see here, where, if you notice, we have all the inner products between AI and BJ. A1B1, A1B2, A1BN, A2B1, A2B2, A2BN. Example, otherwise it will be difficult to make sense of this without a concrete example. Take this matrix A, take this matrix B. My matrix A has these rows. I'll use different colors to make this clear. And my matrix B has these columns. I'm using different colors. So I want to figure out what the result is. First of all, the first matrix is 2 by 2. The second matrix is 2 by 2, so I can multiply them. So the result is also 2 by 2, and it has these four elements: C11, C12, C21, C22. Let's see what these elements are. C11 over here is the result of multiplying A1 times B1. First row, first column is this thing. What is C12? First row, second column. What is C21? Second row, first column. 2, 1, 2, 1. Maybe to help you a little more, this is 1, 2, 1, 2. So C11 is 1, 1. C21 is 2 times 1. When I say times, I mean we multiply the vectors. We know how to multiply the vectors using an inner product. And this inner product I'm using here is the standard inner product. So let's be a little more specific. Take C21. C21 is second row, first column, 3, 4, 0, 2. And the result is, let's break it down, 3 times 0 plus 4 times 2, which is equal to 8, as we have written there. The result is 4, 15, 8, 31. Take your time to go through the arithmetic here to verify that this is correct. On the other hand, AB, we said, is this, 4, 15, 8, 31. If you do BA, you get 3, 4, 23, 32. Nothing to do with one another. Not even one of the elements is the same in these two matrices. They're all different. And you know what? You can do this as an exercise. Take two matrices, put some numbers there arbitrarily. Chances are you will get different results when you do AB and BA. AB is not the same as BA. They are absolutely different things. Be careful with two things when you work with matrices. One is to make sure you have compatible dimensions. This is super important. And the second is to not be confused. Keep in mind AB is not the same as BA. Then, is it possible to take a matrix that is not equal to 0 and then take the square of a matrix? Wait a second, I told you before that you cannot take a vector and square it. That's true. Can you take a matrix and square it? Well, if it is a square matrix, if it is n by n, yes, you can. What is the square of a matrix? A times A. A times A is the square of a matrix. A squared. Now, say A is not the zero matrix. It's not a matrix that has only zeros inside. Can we take the square and end up with a 0? Answer, yes, we can. Example, take this matrix, 0, 1, 0, 0. Do this, 0, 1, 0, 0, squared. What is that? 0, 1, 0, 0, multiply with 0, 1, 0, 0. I won't do this for you. I'll leave this to you as a little exercise. Do this multiplication and you will find that the result is 0. Another question. Is it possible to take a matrix A that is not equal to 0? And preferably, let's say it doesn't contain any zeros as elements. So is it possible that the cube of this matrix is equal to 0, but the square is not equal to 0? Short answer, yes. Here is an example. You can verify this for yourselves. How did I come up with these examples? I will not tell you. You don't care about that. That's my business. The thing is that I'm telling you these as counterexamples, not to be confused. So a squared is 0. If I tell you that a is a number, you'll tell me, okay, so a is 0. But if I tell you that a is a matrix, you have to keep in mind that there are matrices that are not 0, you square them and you get 0. If I tell you a cube is 0 and I tell you a is a number, then you must tell me a is 0. But if you have matrices, a cube is 0 does not imply that a is 0. So that's why I'm giving you these counterexamples. Now some basic identities. I'm not sure how to make this slide not very boring. I'm afraid I'll just have to go through the properties. It's nothing really too exciting here. Most of them are super obvious, like the first one. If you do AB, you compute AB, and then you multiply by C. It's the same as doing BC first, then doing the multiplication A times BC. The order of multiplication doesn't matter. Second property is the distributive property. From the left, A times B plus C is AB plus AC. And then A plus B times C. From the right, now you multiply from the right, is AC plus BC. Oh, by the way, A plus B C is equal to AC plus BC. It is not equal to CA plus CB. For all you know, C times A might be impossible to do because you might have incompatible dimensions. But even if you have compatible dimensions, these things are typically different from one another. Next, we have a plus b squared. This is not extremely obvious, but I would like to leave this to you as an exercise. It is a very simple exercise. All you have to do is to be careful and not to confuse AB with BA. These are not the same thing. So try this as an exercise. It says a plus b squared. It's not a property you need to memorize, by the way. You don't need to memorize this. It's not really an identity you need to have in mind. But a plus b squared is a squared plus b squared plus ab plus ba. Not plus 2ab, plus ab plus ba. When it comes to the transpose, a times b transpose is equal to b transpose a transpose. You swap the two, b transpose times a transpose. X transpose x, first of all, the most important thing here, x transpose x is a number. X transpose x is a number if x is a vector. X transpose x is a real number. X transpose, you can do both. X transpose is a matrix n by n. Why is that? Where did this come from? Well, x is n by 1. And when you transpose it, I should write this here, x is n by 1. When you transpose it, the result is 1 by n. 1 by n times n by 1, and the result is 1 by 1, aka a number. On the other hand, we said that x is n by 1, x transpose is 1 by n, multiply and you get n by n as we wrote down here. This is super important to remember. X transpose x is a number, x transpose is a matrix. What number is this x transpose x? This is also super important. What is this x transpose x? This is the inner product of x with itself, the standard inner product, and this is the squared Euclidean norm. I'll leave this to you. This is not perfectly straightforward to you now. I mean, later it will be. But take some time, go back, recall, check again what is the standard inner product. I don't expect you to remember because I told you like 15 minutes ago. You need to revise that. Again, if there is, that's the point with the flipped classroom approach. I know that while you're watching this video, you don't understand everything. I know that's kind of the objective here. The objective is not for you to understand. It's to be, as I said, to be exposed to the material. And then you'll come to class and we'll solve exercises. We'll be solving exercises for 2 hours. We'll be addressing your questions. We'll be discussing about anything you like. And this way you will really seriously comprehend what we're talking about here. And this will not look like hieroglyphics. But for the time being, embrace the ambiguity, embrace the fact that you don't understand. Try, but it's normal if you don't. Now, x transpose x is a number, which is x times itself, using the inner product, which is equal to the squared norm. Again, go back and recall what the Euclidean norm is, how we defined the Euclidean norm. And x transpose x is a number. X transpose, as I said before, is a matrix. This will be super useful throughout the module. We said that AB is not equal to BA, but there are exceptions. Rare exceptions, but there are exceptions. This is one. A times I is equal to I times A, where I is the identity matrix. Also, if you multiply A times 0, the result is 0. Well, I suppose you expected that. A times 0 is 0. Be careful with the dimensions. Here, I'll write it down as a comment. So, careful with the dimensions. So we said that A is m by n, so 0 must be n by whatever you like, but it must be n by something, otherwise the dimensions will be incompatible. This 0 is the 0 matrix, it has dimensions. Right, and the last thing which we mentioned above, but it's worth repeating, is that x, y, the standard inner product is written like this, x transpose y. You can write x times y like this, you can write x transpose y, whatever floats your boat. Now, just a moment. Before we move on, we just discussed about matrices. Let's take it from the beginning and do a little mini recap. What is a matrix? Sorry, things we can do with matrices. We can add them, we can subtract them. To add them and to subtract them, they must have the same dimensions. Otherwise, it doesn't work if they have incompatible dimensions. You can take a scalar, you can take a matrix, and you can multiply them like this. Like this here. If you have a matrix of dimensions m by k and then b k by whatever you like, then you can multiply them. The number of columns must be equal to the number of rows of a and b respectively. And if it is m by k, k by n, the result is m by n. ab is m by n. I wrote it down here with big font. m by k, k by n is m by n. AB is not the same as BA. How do we do the multiplication? How do we carry out the multiplication of a matrix times another matrix? The result is a matrix that contains all the inner products. It contains the inner products of the form AI times BJ, or as we just said, sorry you can't see that, AI times BJ, or if you prefer, AI transpose BJ is another way to write it. This is an A, my handwriting wasn't really good there. So AI times BJ, and this here is the standard, this is the standard inner product we're using in this case to multiply the vectors. Then we did an example. We did another example. Actually, I'm leaving this to you as an exercise to confirm, really do it, to gain some confidence in matrix multiplication. AB is not the same as BA. Here is an example. A matrix, you can take a matrix which is not 0, you can square it and you can get a 0, which is weird. Or you can take a matrix which is not 0, doesn't have any zeros, you can cube it, and the result is the 0 matrix. Strange again. We mentioned a few properties, and that's it. Now we are ready to move on to section 1.4, which is quadratic forms. What is a quadratic form? This really now doesn't deserve a section of its own because it's a very simple concept. A quadratic form is this function. It has a super fancy name, but it's nothing fancy really. It's you take a matrix A, you take it to be symmetric, and you do x transpose AX. Have a look. X is a vector, is n by 1. A is a matrix, n by n. It is also symmetric. And x transpose is 1 by n. So what is the result? Pause the video to think about it. The result is a simple number, is a scalar. The result is a scalar. So this function f takes, pay attention to the notation we're using here, takes a vector as an argument and returns a number. You have to give it, it's asking for a vector and it gives you back a number. I find this notation here very close to a computer science / programming way of thinking, where you specify what the inputs and the outputs of the function are. So here we give a vector, the function returns a scalar. Right, what about this function? First of all, it has a name. It is called a quadratic form. What about these quadratic forms? In some cases, for appropriate matrices A, whatever x you put here, whatever, it can be a vector that has positive entries, it can be a vector that has both positive and negative, or it can have only negative entries. It doesn't matter. The result x transpose AX in some cases will be not negative. It'll be positive or 0. Look, for every x, not for one simple example you were lucky to find, for every x. In these cases, we say that the matrix is positive semi-definite. I'll give you a super simple example with which you can relate. Take A to be this symmetric matrix, the identity. Then if you do x transpose AX, which is x transpose identity x, well, identity times x is x. So it is x transpose x. You've seen this before. You've seen x transpose x before. If you like, pause the video, think about it for a moment, or go back and check where we encountered x transpose x last time. We said it's a number. Yes, it is a number indeed. So this is the norm, the Euclidean norm of x squared. It's a square of a number. The square of a number is non-negative. So this matrix I, this matrix here, is a positive semi-definite matrix. Okay, and there is a special notation for this thing so that we don't have to write A is a positive semi-definite matrix. We have better things to do in life, so that's why we write that A belongs to Sn plus. We put a plus to remind us of the thing that it is positive semi-definite. I'll now move on to debunking a couple of misconceptions about positive semi-definite matrices, but first of all, let me add one more. Let me put on the table another definition, that of a positive definite matrix. So now, if you take a matrix A that has the property we just discussed, and it has an additional property, if x transpose A happens to be 0, then x is 0. To put it differently, in simple words, the only way to get a 0 out of x transpose AX, the only x that satisfies x transpose AX is 0, is the 0 vector. Put anything else you like, you will not get a 0. The only way to get a 0, the only way for x transpose AX to be 0 is for x to be 0. If this is the case, it's not always the case, if this is the case, matrix A is called positive definite, and in that case we denote like this: A belongs to Sn plus plus. Some people like this notation: A squiggly curvy larger than equal 0, and likewise here A strange larger than curvy larger than 0. But even if you write A larger than equals 0, you read A is a positive semi-definite matrix, and you read this as A is a positive definite matrix. Before we move on, let me just remind you once again, we are focusing only on symmetric matrices. If A is not symmetric, there is no discussion. Okay, we're not discussing about matrices that are not symmetric. Examples, a few examples. 0, the 0 matrix is positive semi-definite. Let's see why. Because take x transpose 0, the 0 matrix X. Well, it's very easy to see that this is 0. What makes a matrix positive semi-definite? If the quadratic form is always larger than or equal 0. 0 is always larger than or equal 0. It is actually equal to 0. So 0 is trivially a positive semi-definite matrix. The identity matrix is positive definite. It is not just positive semi-definite, it is also positive definite. The identity matrix is symmetric, positive, definite, or the identity matrix is symmetric, positive, definite. Why? I'll leave this to you. If A is written like this, B transpose B, then A is a symmetric, positive, semi-definite matrix. If you can find the matrix B such that A is B transpose B, then A is symmetric, positive, semi-definite. And here is the explanation why, but I would rather that we now go through a few examples quickly and then you come to class and we'll discuss in more detail in class. I don't want this to be a super lengthy video. So, I said a few minutes ago that I am going to debunk a few misconceptions about positive semi-definite and positive definite matrices, and this is a very famous one. So people tend to believe, because there is the word positive in the name of these matrices, that a matrix is positive definite if all of its elements are positive. Is that right? Well, take this matrix A. All of its elements are positive. Now take this vector x. I'm choosing it to be -1, 1. Why? Because I can choose it to be whatever I like. Do x transpose AX and you get -2, which is not larger than or equal 0. It is negative. So this matrix is not positive semi-definite. Please don't say negative semi-definite. Don't say that. Say not positive semi-definite. Negative semi-definite means something else, something entirely different that we will not discuss. Okay, but the thing is that this matrix is not positive semi-definite. It would be if it had the property that, so this matrix, it is not. It would be if it satisfied the property x transpose AX is larger than or equal for all x, for all vectors x. Yeah, but too bad. I found the vector x and I did x transpose AX and I got a negative number. So what I was trying to say here with this example is that the fact that all the entries, all the elements of A are positive doesn't mean that matrix A is positive semi-definite or anything. Another example, this matrix 1, 1, 1, 1 is not positive definite, but it is positive semi-definite. Why? Just a moment. This matrix is positive semi-definite, but it is not positive definite. Let's see why. Take a vector, any vector you like, x1, x2, and do x transpose AX. You will find, I will leave this to you as a little exercise, it's not difficult to do this, to prove this equality as an exercise. You can find that this is equal to x1 plus x2 squared. It is a square, so it is always not negative. But if you choose x1 to be equal to minus x2, so for example, if you choose the vector, I don't know, 1 to 3, minus 1 to 3, or whatever you like, then x transpose AX is 0, and x is not the 0 vector, so it is not positive definite. Another misconception, if a matrix is positive definite, all of its elements are positive. Wait, isn't that the same as what we did before? No, it isn't. What we did before was a matrix is positive definite if the elements are positive. We debunked this. So we found a matrix here which is not positive definite. It is not positive definite, but all of the elements are positive. Now I'm going to give you a matrix that is positive semi-definite or definite, but it contains negative elements. There you go. This matrix is positive definite, not just semi-definite. This matrix is positive definite. You forgot what this means. Okay, that's fine. X transpose AX is always positive or 0 for all x in Rn. And if this quantity is 0, this means that x is 0. The only way for x transpose AX to be 0 is if you take the 0 vector. You will not find a non-zero vector that annihilates the quadratic form. Why is this positive definite? I'm not going to tell you, but you can either trust me or you can try to disprove it. Find as a challenge that is impossible to carry out. Find a vector x. You can take it to have positive entries, negative entries, whatever you like, I don't care. Find an x such that x transpose AX is negative. Sorry, you cannot do that. But why is this positive definite? How do I know it's positive definite? We'll get there later. I cannot tell you now. Trust me for now, and we'll see later why this is indeed positive definite. To tell you the conditions under which a matrix is positive definite or positive semi-definite, I must first define the concept of an eigenvalue of a matrix, but I don't want to do this in this video because it will become too long. We'll do this later. Just a few things. We're now approaching the end of today's video. If you take a matrix Q or A, doesn't matter, which is positive semi-definite, symmetric and positive semi-definite, positive definite, then you can define a norm, which is, as we say, induced by this matrix Q. So, bottom line, give me a matrix Q, which is positive definite, and I can construct a norm from it. I can use this matrix Q to construct a norm. What norm is that? It is this thing, square root of x transpose qx. Why is this a norm? Well, go back to the definition of a norm, and actually that's a good exercise. Prove that this is a norm. By the way, you can also use this matrix Q to construct a very special inner product, x comma y with the matrix Q is equal to x transpose q y. And in fact, this inner product is has a very intimate relationship with this norm. This norm is induced by this inner product, as we said before. These norms, this type of norms, are extremely useful both in control and in estimation theory. In control are used to study stability, they are used to design controllers. In estimation theory, they are used to design estimators, they're used in statistics, in machine learning, they're used absolutely everywhere. They are norms that we can construct using matrices. The inner product I mentioned earlier, I have it on this slide as well. And that's it for today. I don't want us to go into the inverse and the completion of squares. We'll do this in a separate video. Thank you very much for watching. You must have questions, I'm sure about it. Come to class this week and we'll discuss whatever you like. And we'll be solving exercises for 2 hours. So hopefully you will leave the class without significant obscure points. So once again, thank you very much for watching, and I'll see you later. Goodbye.